Hello and welcome to this video lesson. This video lesson will focus on the mighty topic of the slope. Slope or gradient is one of the most important topics in math, and it's one that's used in many different fields, including any experimental science, social sciences, business, and really in math, starting from simple linear functions all the way to very challenging calculus and vector problems. One definition of slope is the rate at which the dependent variable changes with respect to the independent variable. In this example over here, we have on the y-axis, or our dependent variable is money, and in the x-axis, or our independent variable, is time. Money is measured in dollars and time is measured in months. We have three students. We have Joey, and if you look at money that he has in his bank account, kind of starts around this region. We don't have any values, but you can see that it's somewhere in the middle area here, and he keeps making some money every month, so he's kind of increasing the amount of money that he has. When we look at Angela, Angela starts lower than Joey, but then is making a lot of money every month, and her bank account is actually filling up pretty well. We have Greg over here who starts pretty high, but then every month Greg is spending a lot of money and is actually decreasing the amount of money that he has in his account every month. And finally, we can see Jackie, and Jackie kind of starts here, and his money kind of stays steady. It doesn't really change. So it's not really, on average, he's not really spending that much money, or he's not really gaining any money. So the amount of money he's spending is same as the amount of money that he is gaining every month. So the slope, or our gradient, is the rate at which the dependent variable changes with respect to the independent. And in this case, in this example, again, our dependent is money and our independent is time. So in this particular example, our slope will help us figure out what is the rate at which money changes per unit time, or how much monies are these individuals gaining or losing every month, because our unit time over here is month. Another way that mathematicians look at the word slope is that this is a number that describes the steepness and direction of a relationship. So, for example, in this graph over here, we have the amount of money that people have every month, and we have Angela first over here. And if I were to draw a straight line that goes through all the points, we can kind of see that it forms a nice straight line, and I'm going to do that for every individual. And we can see that one of the steepest line, or two of the steepest lines in this case, are the relationship for Angela and for Greg. We can see that both of those are pretty steep. We can see that Jackie's over here doesn't actually change at all. It's pretty flat. It's kind of like a horizontal line which has no steepness. And Joey over here, you can see that the amount of money that he's making is actually increasing, but it's not that steep. So the slope is a number that describes both steepness and direction of the relationship. So in terms of direction, if you remember from previous topic of statistics, a direction is positive if, as the independent variable, in this case time, is increasing, the dependent variable, in this example money, is also increasing. So if one is if independent is increasing and dependent is increasing all the time, we call that a positive relationship. And the relationship is negative if, as our independent is increasing, our dependent is actually decreasing, like this. So you can see one line is slanted in this direction, so it's kind of sloping upwards, and the other one is kind of have a steepness which is going downward. So positive steepness and negative steepness. So this number, or our slope, will describe both the steepness, so high steepness, positive, and the direction, so positive and negative. So if I put a few numbers here, so I'm going to put a number 7, -5, 2, and 0. And if we were to match these numbers to our lines over here, or our individuals in terms of their slope, we would actually look at the definition. The definition says that the number describes steepness and direction. So I can see that 7 is a high value, so it must have a high steepness. -5 has a high steepness, the value is still very high. 2 is a smaller value, it's not as big as 5 or 7, and 0 has literally 0 steepness. So, and in terms of direction, if it's positive, like 7 or 2, that means that it's sloping upwards, or the steepness is upwards, or as independent variable is increasing, dependent is also increasing. And if it's negative, it means it's a negative relationship. That means that if independent is increasing, dependent is decreasing. So to match the numbers, first of all, we can see that the only relationship which is negative, so as the independent is increasing, dependent is decreasing, is our purple line over here, which is Greg. So we can kind of label the -5 as Greg. We can see in terms of our slopes, or in terms of our steepness, we can see that Angela here has a very high steepness and it's positive, and we can see Joey also has a positive one, but not nearly as steep. So we know that this 7 will belong to Angela, and our slope of 2 will belong to Joey. And finally, we can see that this blue line over here actually has 0 steepness, meaning that, we can see that nothing is actually changing. So the 0 slope means no change. So we can say that this one actually belongs to Jackie. When we look at these numbers, we can also understand one other thing. So going back to the first definition, we can see that this number is the rate at which the money is changing per unit time. So it means how much money each person is making or losing every month. So we can see that every month, Angela is making $7. So in 1 month, she would make $7. Greg is losing, because it's negative, $5 every month. So Greg over here every month loses $5, and then loses $5 again, and loses $5 again. Joey makes $2 every month, and Jackie makes $0 every month. Let's look at a few ways that we can actually calculate the slope. So here I have a relationship. This is kind of like a different relationship than I had last time, but it's still Angela, and Angela again is making some money every month. So we can see that it's a positive correlation. So as our independent variable, which is time, is increasing, our dependent variable, which is money, is also increasing. I will actually draw a line that will go through all these lines just so you can kind of see how the relationship looks like, and I'm going to draw it pretty thin so you can still see the points. So the slope again is the rate of change in money every month. So we want to see how much money is Angela making every month. And looking at this graph right away, we can actually see it. We can see that in one month, she went from $100 to $150. So we can easily calculating it by looking at the graph, looking at the line and saying, oh, okay, so at this point over here, and we have to pick points from the line, and in this case all our points lie on the line, so we can actually use this point. We can see at this point, at month 1 she had $100, and in month 2 she has $152. So in 1 month she made $50. So again, the first way to figure out slope is actually just doing that, looking at the line and going by 1 unit in our independent variable and going and seeing what's the change in our dependent variable, in this case 50. The other way that we can do this is actually looking between 2 points. And this is a little bit easier when you have a lot of data and if you actually draw a line of best fit. So in this case, I'm going to look at 2 points, one over here and one over here. And I am going to look at the change in my dependent variable, which is this over here. And this is a change in time. And if you're not familiar with the notation, this delta sign over here, I'm just going to write it down here. Delta means change, the triangle sign. So this is kind of change in time or change in my independent variable. And my dependence is this change over here. So I need to kind of erase this part and redraw it. And this is change in amount of money. So I'm just going to use a dollar sign for it right now. So the slope is the rate at which our dependent variable or our money is changing with respect to our independent, which in this case is time. So to write an equation for this, we can write it as slope is equal to how, or change in dollars in here, divided by change in time. And another way that people often write this is using a notation that this part over here is kind of how much you're rising. So from here to here, you're actually rising by this amount, which is exactly the same amount of in here. So I'm going to call this rise. And this value over here is the amount that you run. So from here to here, you're actually running this much. So this is the horizontal movement. We call this run. And the vertical movement, we call this rise. So another way or easier way to remember the definition of slope is rise over run. So now looking at the graph to figure out what the change in our amount of dollar is, we can actually kind of look at this area here. We can see that the change is from 100 to 300. So meaning if we want to find this change, I have to subtract 300 from 100. So the change over here is equal to 300 minus 100. And the change in time, in this case over here, is I'm starting from month 1 and I'm going all the way to year or month 5. So the change is 5 minus 1. So I can simply write 5 minus 1. And if I do the calculation, 300 minus 100 is 200, and 5 minus 1 is 4. And if I divide that out, I actually get 50. And to write my units for this, I know the unit in my dependent variable is dollar, and the unit for my independent variable is months. So I can just write it as dollar per months. Using the green method, which is rise over run, it's the same idea. Our change in dollars over here is our rise, so we're going from 100 all the way to 300. So that is equal to 200. And our change in time, we're going from 1 to 5, so that's 4. So I can do 200 over 4. Actually, I'll write that here so that you guys don't confuse it. So this is 200 over 4, which is equal to 50. So I should get the exact same thing, and it's the same unit, dollars per month. Now, one other way that you can actually find slope that I will show you in this video is using 2 points. And what I want to do is make sure that you know different methods of calculating for slope and actually using the most efficient one whenever possible. So the last method that I'm discussing today involves 2 points. So on your line, you can actually pick any 2 points. So you can pick a point right here, right here. You can pick one right here, or pretty much anywhere. So in this case, I will pick 1 point right here, our starting point, and I will choose our final point over here. To label them, this point over here, I'm going to call it P1. And this point has coordinates in my independent variable of 1. And in my dependent variable, it has a coordinate of 100. And just for the sake of making this a little bit easier, I am going to call this axis X and call this axis Y. And by doing that, this coordinate over here, which refers to my x value, right here, x value of 1, I am going to give it a subscript of 1, which corresponds to the same subscript that I gave my point. So point 1 will have x coordinate of 1, and it will have y coordinate of 100. So again, point 1, the subscript 1 refers to point 1. This x value over here is x1 because it's the x coordinate of point 1. And this value over here is the y value of point 1. So that's where the subscripts are. So for my point 2 over here, this one over here, I'm going to call it point 2. And the x value here is 5. So I'm going to label this as 5. And the y value is approximately 300. So I'm going to label this as 300. I will call this x2 and y2, referring to the x and y coordinate of point 2. So notice that when we were solving for our slope originally, we used the value of 300 here, which is my y2, and we subtracted it from 100, which is my y1 over here. So our slope given 2 points, so given point x1, y1, and point 2, x2, y2, We can find our slope using the equation of change in y over change in x, which is same as y2 minus y1. So once again, when we were looking originally, our y2 value is this one over here, and our y1 value is the one over here, over, or divided by, the change in x. So how much the x is changing. So it's changing from 5, it's going from 1 to 5. So to find the change, we subtract 1 from 5. So it will become 5 minus 1. So I can write that as divided by x2 minus x1. So in our example again, x1 is 1, y1 is 100, x2 is 5, and y2 is 300. So using our equation over here, y2 is 300 minus y1, which is 100, divided by x2, which is 5, minus x1, which is 1. And solving for this will end up giving us 200 over 4, or just $50 per month. And this is the equation that we're mostly going to use in our course, which is delta y over delta x, or y2 minus y1 over x2 minus x1. Two side notes just before we do a few examples on how we can find slope using different methods. The first one is how we can manipulate different graphs to show different things. So for example, over here we have two graphs, and you can see that in the first one we have time, well, in both of them we have time on the x or the horizontal axis and money on our vertical axis, or this is our dependent and this is our independent. And we can see that the points are actually the exact same points. So for example, our point 1 is at 115, and here is 115. And our second point is 220, 220, 325, and 430, and 325, and 430. So we have the exact same points. The only difference is how we are using two different forms to represent our mathematics. And one of the reasons you folks are learning mathematics is to become critical thinkers. And I want you folks to really be able to recognize different forms of mathematics, because they can be used to manipulate data sometimes, and you got to be aware of that. So in the first situation over here, again, the data is exactly the same, but when you look at this one, you can see that the slope of how much money you're making over here, if we didn't have the numbers over here, if we had erased all the numbers, you could see that the slope is actually not nearly as steep as this one over here. So if I didn't have any of the numbers, if I blocked all these numbers, I would think that in this situation, this person is actually making much more money every month, or sorry, this one over here, the person is making much more money every month than this person over here. But we have to be aware that, oh, this graph actually has a different starting point and a different scale. You can see that the x-axis is much more squished together, making it possible to get a bigger slope. You can see that the y is the y-axis, or the vertical axis, is much more stretched, allowing to get a much steeper looking slope. And that's why the other form of mathematics in this case has to be used to show what the slope actually is, for you folks to be able to make a good comparison. Since I have the same points over here, I'm going to use 2 points to actually find the slope. So this point over here, for example, is 0.220, and this point over here is 0.430. So if I were to find the slope, I'm going to use 0.1, 220, and 0.2, 0.430. I am just going to label this as x1, this as y1, and this as x2, and this as y2. I will now use my equation, slope or gradient. I'll just write slope is equal to y2 minus y1 over x2 minus x1, or you can use delta y over delta x. Now my y2 value is 30, and my y1 is 20, my x2 is 4, and my x1 is 2. And again, the subscript refers to the point, so this is x coordinate of 0.1, and this is y coordinate of 0.1. So plugging in all my values, y2 is 30, y1 is 20, x2 is 4, and x1 is 2. So subtracting that, I get 10 over 2, which is equal to 5. And my unit, again in this case, are dollars per month. So in both cases, you can see that the slope is actually the same. The slope is $5 per month, meaning that in both cases, the person is making $5 every single month. But the representation looks slightly different. You can see that just by looking at it, looking at this graph versus this graph, you would think if you didn't have the value, or if you didn't have another form of representation of the slope, you would just simply think that this person is making more money. So just be aware of these situations. One other concept that I wanted to cover before we do the example is this graph over here, which is graph of position versus time. The slope in this type of graph actually has a very special meaning. So let's say here you're starting at a certain position, and with time you can see that your position is actually increasing. And the rate of change of your position versus time in this case actually signifies how fast you're going. And in this case, it kind of signifies your speed, or what we call velocity. But let's keep with speed for this particular example. If I have a non-linear relationship, and this is one good example of that, you can see that it doesn't follow a straight line, it's actually a curve. So in this case, it's kind of a curved line, or non-linear as not a straight line. If we were to find the slope between 2 points, let's take our starting point and the end point over here. So I'm going to take this point and this point, and if I were to find the slope over here, that means I have to draw a straight line, and the slope of this line, or how steep this is, will signify how fast I went between, or on average how fast I went between 0.1 and between 0.2, which this is 0.1 and this is 0.2. So the slope between 2 points is the average speed. So for example, if this time over here, if this time over here was 1 and this time over here was 10, and my position here was at 15 meters, and my position over here was, let's say, 33 meters. if I were to find the slope between these 2 points, and let's just do this. This is another good example. So my point over here is 115, and my point over here is 1033. And slope is change in y over change in x. So this is x1, y1, and this is x2, y2. So my slope would be y2 minus y1 over x2 minus x1. And once I plug in my values, I get 33 minus 15 divided by 10 minus 1. On the numerator, I get 18, and on the denominator, I get 9. With an arrow over here, 18 divided by 9 is just 2, and my units are meters per minute. So that means every 1 minute, I travel 2 minutes, and this is on average. So therefore, average speed is 2 meters per minute. Note that the word average is very important in this case because this is just our average speed. Because if we look, we can see that from here to here, I'm not actually traveling at a constant speed. From here to here, I'm actually traveling a lot of distance every minute. So I'm actually going really fast around this point. And then I'm kind of slowing down. So from here to here, I haven't traveled much over this distance. So around here, my speed has actually decreased. Right about this area, from here to here, you can see that I haven't actually traveled anything in this distance. Over here, I kind of have like 0 speed, and then it kind of seems like I'm traveling backwards. Now, I don't know what the reason for that would be in this case, but I kind of have a negative speed in this case. Not very steep again, so you can kind of see the steepness is very high over here. Steepness starts to decrease a little bit, and steepness is 0 right around this point, and it starts to decrease again around this point. So this slope that we find over here is kind of on average how fast I went, and if we wanted a particular, or if we want the instantaneous speed, what we actually have to draw out is what's called a tangent. And we're not going to cover this in detail on this course here, but if I were to draw a line that kind of represents my slope at this point, it would be a line like this. And at this point over here, my instantaneous could be kind of, if I were to draw one line that would represent my slope, it would be this line over here. So to find our instantaneous speed, we have to draw a tangent and actually find the steepness of that using 2 points. So once I draw this line, and it's kind of an estimate, I can't really do a perfect job drawing a tangent, but then I can choose 2 points on it and actually find the slope. And you can see the slope of this line is actually much steeper than this one, meaning that I'm traveling much faster at this point than my average speed. You can see that slope here is 0. It's actually a flat line. So I'm not traveling, I literally have stopped at this point, and I'm actually going negative at a negative speed over here. And it kind of makes sense because first I'm traveling faster than my average speed, and then I'm traveling slower, and I'm actually moving backwards. So the speed keeps changing. However, this slope over here, which is my average speed, will give me a good representation of how fast I kind of went on average from time 1 all the way to time 10. Okay, let's do 2 sets of examples. So for the first example, we want to find the slope of all these lines given to us. And we can use points, or an easier method for this is just using our equation of rise over run. So what we have to do is we have to start from one of the points. It doesn't matter which point we start from, and get to the other point. So slope is equal to rise over run. So I'll just write that down for now, rise over run. So we're going to count our rise and we're going to count our run. Starting from this point over here, which is the bottom left, and I would have to run by 1, 2, 3, 4, 5, 6, and I would have to, so plus 6, and I would have to go up by 1, 2, 3, 4, 5, and 6. So positive 6. So this is 6 over 6, which is equal to 1. Now, starting from this point, I could have actually just started rising first. So 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And you can see that it's still the exact same values, 6 over 6, which will give me 1. So it doesn't really matter how you rise or run, or even from which point you start to rise and run, you should still always get the same slope. For line 2, so slope again is equal to rise over run. Just to show you that it doesn't matter which point we start from, I'm going to start here, but you just have to remember that you have to start from one point and get to the other point. Sometimes students kind of say that I want to go from here to here, and then kind of start going up from here, and then they go left from this point. So you have to start from the same point and end in your second point. So in this case, first point is top right corner, and to get to my other point, I have to rise by -1, -2, -3, -4, -5, -6, so -6, and -1, -2, and -3. So my rise here is -6, and my run is -3, and dividing the two will give me +2 as my slope. Now, if I had started from this point, I should get the same value. Let's try it. I will get rise of 1, 2, 3, 4, 5, and 6, so +6, and 1, 2, 3. Since I'm going to the right is positive. So once again, actually, I forgot to mention this. If you're going to the right is positive. If you're going to the left is negative. If you're rising up is positive, and when you're rising downwards it's negative. So in this case, using blue, if I use the same equation, I get my rise is 6 and my run is 3, and dividing the two, I should get the same value, and I do. I get 2. For my next one, I am going to start from this point over here. I'm going to start with my run. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So +12 is my run. So rise over run. My run is 12. And my rise, I have to go up by 1, 2, 3, 4, 5, and 6. So +6, so 6 over 12 simplifies to 1 over 2. Finally, for the very last one, I am going to start from this point and get to the bottom right corner. And to do this, I have to go down by 1, 2, 3, 4, 5, 6. So my rise is -6 because I'm going down, and then I have to go 2 to the right. So my rise over run is equal to -6 over +2, and that will end up giving me -3 as my final answer. So all of these lines actually have the same grid and the same scaling. So just to check our answer, we can see that This line has the lowest steepness, and we can see that it's 1 over 2 compared to 3, 2, and 1. So this one actually does have the smaller steepness, and it makes sense in terms of the slope value. This one has the next steepest line. This one is steeper than this, so 2 and 1. All these are positive, so as our dependent is increasing, or sorry, as our independent is increasing, our dependent is also increasing, which is the case for all of these three, but this one is opposite. As our dependent is increasing, our dependent is, yeah, as our independent is increasing, our dependent is actually decreasing. So this one is actually negative. So the negative sign also makes sense. And this one, in terms of steepness, this is actually steeper than this one over here. So you see the 3 and you see the 2. So everything actually makes sense. So always check your answers, especially in terms of direction. If the steepness is going down, or if as your independent variable is increasing, your dependent is decreasing, then you should have a negative value. Let's do one other example here, which is divided into 3 parts, and we're trying to calculate the slope of a line that passes through these points. So for our first example, our point is 1, 3, and 2, 5. So let's call this our point 1 and this one as point 2. This would be my x1, y1, and x2, y2. So slope is equal to delta y over delta x, or you can write this as y2 minus y1 over x2 minus x1. And if you're given 2 points, it's easiest to just use this equation. So my y2 over here is 5, my y1 is 3, my x2 is 2, and x1 is 1. So I get 5 minus 3, which gives me 2, and 2 minus 1, which gives me 1, and I have to simplify this to its simplest form, which is just 2. In terms of what you have to include in terms of your steps, it really depends on what level of math you're at. So if you're just being introduced to this, then a lot of teachers would expect you to have this first step, this one, and some calculations sometimes in the final step. In the year that I'm teaching it right now, the steps that I kind of expect is slope being equal to this method mark being included in terms of you having the proper equation and proper numbers plugged in terms of accuracy of values, and then doing some sort of calculation over here depending on the difficulty. This could be an implied method mark, or it could be a required method mark, and finally getting a final solution as an accuracy mark. For the second question, I'm going to do the exact same step. I'm going to label these as point 1 and point 2. It doesn't matter which one you label as point 1 and point 2. This will be x1, y1, and x2, y2. And my slope equation is delta y over delta x. I'm going to skip the step that actually expands the equation to y2 minus y1 over x2 minus x1, and I'm just going to start plugging in the values. My y2 value is negative 4. My y1 value is negative 1. I'm going to make sure that I put this in brackets just so that I can distinguish that, oh, the negative and negative are going to make a positive. And when I divide it, it's delta x, meaning x2 minus x1, so that's negative 3 minus 2. So in terms of calculation, just doing it in 2 steps here, this is same as negative 4 plus 1, and negative 3 minus negative 2 is negative 5. And when I do the calculation on the numerator, I get negative 3, and the denominator I have negative 5, which simplifies to 3 over 5, positive 3 over 5, because I have two negatives which are canceling each other out. And in terms of step here, method mark and proper accurate values actually plugged in is very important. Sometimes this could be an A2 depending on the situation. So sometimes we look at the accuracy of the numerator and accuracy of the denominator. Sometimes depending on what the values are, we might just look at the accuracy of all values put into together. And we're kind of looking for, in this case, the numbers are a little bit more challenging because you have minus a negative value. So you could, again, this one is not too challenging, so I'm going to give an implied method mark and finally an accuracy mark for a final answer. And again, the most common mistake for a question like this would be this step over here, which is the negative 4 minus negative 1. A lot of students would just put minus 1 over here and lose an accuracy mark here and lose a final accuracy mark for their final answer. Finally, the last example over here, we're going to use the exact same method. This time I'm going to label things differently, 0.2 and 0.1, just to show you that it works the exact same way. This will now be x2 and x1 and y2, and this would be x1 and y1. And again, I have to make sure that my subscript here correspond to my proper point. So this is 0.2 will have x coordinate 2, y coordinate of 2. And 0.1 will have x coordinate of 1 and y coordinate of 1. And again, one common mistake is students labeling, like for example, for this point, they would label this as x1, x2, and y1, y2. But you have to remember that in a coordinate, when we are labeling a point, mathematically, we put the x value first and y value second. Now, plugging everything into my equation, my slope will equal to delta y over delta x, which is equal to my y2 value, which is 1, minus my y1, which is 2 over 3, over, and I have x2, which is 1 over 2, minus x1, which is 3. You can already see that this one is a little bit more involved in terms of steps. So here I'm going to get a common denominator, 3 over 3 minus 2 over 3, and 1 over 2 minus 6 over 2. And I will end up getting 1 over 3 divided by negative 5 over 2. And I will simplify this and write it in as an actual division. This is saying 1 over 3 divided by negative 5 over 2, which is same as 1 over 3. I can change the division to multiplication and flip my denominator and numerator, or take the reciprocal, and I should end up getting 2. So my numerators will multiply together. 1 times 2 is, actually 1 times negative 2 here is negative 2, and 3 times 5 is 15. So I get negative 2 over 15. And that's the most simplest form I can actually write this as. And again, depending on your math skills and how much practice you're having, you might be able to you might be able to go from here to here without actually going through these steps. And you can use the shortcut that you can actually do numerator here multiplied by the biggest denominator will give you this value. and the closest ones 3 and 5 multiply to give you the denominator. But again, if you're not comfortable with that shortcut, because that's just a shortcut, it doesn't work for everything, you should actually go through the long process. In terms of marking, this one will involve method mark and accuracy mark. Another method mark will actually go to this whole step over here. This one, in terms of method, it will involve method mark just because it involves fraction, and it's actually a little bit more challenging. So one method mark for actually properly subtracting things, an accuracy mark for actually getting to this step, and another method mark which is kind of implied to get to your final answer over here. So again, this question over here, because it involves fraction, is much more involved, but you should be able to solve questions involving fractions. You don't really have to watch this part of the video. It's a little bit more, I wouldn't say enhancement, but it will, it's a little bit of a real life example. It's actually pretty useful. If you have time, you can actually watch it. In this case, we actually have the CO2 emissions calculated in units of metric tons per capita, and on my x-axis over here, or on the horizontal line, I have time in years, and it's plotted for two different countries, Canada and Denmark. And the data was actually collected from worldbank.org, and I kind of put the website over here so you can actually access it if you want. There's a lot of good information in this website. And the reason for this portion of the video is just to give you some idea about how you can look at data and what things you should actually look for. You can see that in this set of data, it kind of starts from 1960, the data collection, and goes all the way to 2014. And there's always limitation to this set of data on how they're actually being collected, where they're being collected. Are all the informations there? How was the method of the data collection? And all these things that you need to actually take into consideration. So the data over here is probably as accurate as it can be, but there's a lot of limitations to that set of data. So you can't say that this is perfect set of data. This is just a set of information that's available for you to kind of analyze and kind of see different trends. Now, we can see that in both of these countries, both Canada and Denmark, there was a rise in carbon dioxide emission between the years of 1960 and 1970. And if I were to draw kind of like a line of best fits, in here it would kind of look like this. And if I were to draw it for Denmark, it would kind of look like this. And these two graphs right now are actually both at about the same scale. I don't think I've done a perfect job in drawing my line of best fit, but it's kind of good approximation. And you can see that even though Canada and Denmark both have different values, Canada actually has higher CO2 emissions between these years. You can see that the rate at which CO2 emission is changing every year is actually approximately the same between the two countries between those years, between 1960 and 1970. So the data sometimes can actually be chunked, and you can kind of manipulate data like that. But what you want to do in here, kind of talk about what is happening in the between 1960s and 1970s. You can actually go and look at the history and kind of come up with different ideas as to why it is that the carbon dioxide emission is actually increasing during these years. But the most interesting fact about this is the fact that actually it's approximately very, very similar slopes during this time, meaning that the CO2 emission for every year, or the increase in CO2 emission every year, is the same for both of these countries. Now, you can see a lot of different changes happening between 1970s all the way to approximately 2000. You can see for Canada, if I were to draw a line of best fit, the trend is pretty much, it's very similar, it's pretty static. Nothing is really changing during these years. So if I were to kind of draw a line of best fit, and again, I'm not doing a perfect job with this. With a computer, you can actually do a much better job. You would actually see that between these years, not much is happening. Let's say up to this point over here, the line of best fit kind of looks like this. So between approximately 1970 to 2010, you can see that the CO2 emission didn't change. So actually, that might be a good thing or a bad thing depending on how you're interpreting this. So if you are thinking that the emission should be decreasing, this is a bad sign, meaning that, oh, it's actually not changing, so that's not a good thing. However, if you actually take into account that, oh, the slope was actually pretty high between 1960 to 1970, so there was a high increase, and then all of a sudden, the increase we managed to change that increase to 0, so nothing has been changing. Obviously, it has been changing, but not by much between these years. And that's approximately 40 years that we kind of kept it at the same value. And if we didn't change something in our system, this would actually increase, and right now we would have a huge CO2 emission. So this is actually a good sign, but again, you can interpret it in many different ways depending on the situation. And you can see that the same trend is actually happening in Denmark. So if I draw a different line, approximately between 1970s to approximately 2000, I would say, if I were to draw a line of best fit, it will look pretty flat. But you can see that there's this, the flat line over here kind of stops at 2000. And starting 2000, we kind of get a negative slope over here. And that's kind of starting to happen for Canada as well, but it's happening a little bit later. It's starting to happen, actually, if I draw a better line, it kind of looks like that. You can kind of see that it's starting to happen about year 2000, I would say about 2008 rather than 2000. So it's better late than never. So it's happening, but it's happening a little bit later than Denmark. So again, looking at these two slopes over here, looking at the trends, you can see that, oh, the slopes here are approximately the same. So if I were to actually take 2 points and find my slope, I can actually do that. I'm going to find the slope of the first green line, and my 2 points are going to be approximately this point over here, which is year 1960 for my x value, and my y value is approximately 6. And again, this is a big approximation. And this point over here, which is approximately 1970, and the emission of approximately 13 metric tons per capita. And if I were to find the slope for that line, it would be 13 minus 6 divided by 1970 minus 1960. So that would give me approximately 7 over 10 as my slope. And the slope for Canada, very similar. I'm going to calculate it using red for the first one. And I am going to take 2 points. I'm going to take this point, which is 1960 and approximately 10 for my y value. And I'm going to take one other point, this one over here, approximately 1970 and approximately 16. So if I were to take the slope over here, I would get 16 minus 10 over the difference between 1970 and 1960, which is 10 years. So I would get approximately 6 over 10. So you can see that the slopes are very, very, very similar. They're almost actually parallel, or actually exact same slope in this case. And in the second part of it here, you can see that the slope of both of them are approximately 0. And Canada keeps this slope for a little bit longer than Denmark, and then Denmark starts a little bit earlier in reducing their CO2 emission, and since 2000 it has decreased it pretty significantly. You can actually find the slope over here to kind of get an idea about what the rate of change is. And you can see that Canada is starting to do the same, and you can see that our slope, if we were to draw a line of best fit, and again, my line of best fits are not by far not the best, you can see that they're approximately the same. So Canada started a little bit later, but we are actually doing a pretty good job with reducing our CO2 emissions. And again, this is just a little bit of an extension of how you can use the slope to kind of compare different scenarios, and in this case, we're kind of comparing CO2 emissions between two different countries. So I wanted to make a short video on slope, but it actually ended up being pretty long, but we did cover a good chunk of information. So I want to I hope that it actually helped you understand what slope means, that you now know that you can use different methods of solving for slope or calculating the value of the slope, and that you know that the value actually shows how steep a line is, and it also shows the direction, whether it's negative or positive, and it kind of actually correlates with correlation. If it's negative, it means that you have a negative correlation. If it's positive, it means that you have a positive correlation between the set of your data. And I hope the video kind of gave you an idea in terms of thinking critically before you're making any decision or comparison. For example, if you have two different graphs, you not only have to look at the scaling of the independent and dependent variable, but you also, it's really good idea to actually sometimes calculate the slope value in order to get a better idea, because graphs can be represented differently in order to trick you sometimes, so you have to keep that into consideration. Finally, for the very last graph, I originally wanted to add Australia in there, but I kind of removed it just to make the example a little bit simpler. So my title is incorrect over here. So this is just Canada and Denmark. I hope the video was helpful.